In this video, we show another example of working a problem out by row reduction with a different kind of solution. So we have this system we want to solve using row reduction or a state that has no solution. x1 plus 2x2 plus 2x3 is minus 7. 5x1 plus 9x2 plus 11x3 is minus 31. Negative x1 minus x2 minus 3x3 is 3. So as always, we start by setting up the augmented matrix form of this problem and then trying to row reduce it. There's our augmented form. We already have a 1 in the top left corner, so I'm not going to mess with that. I'm going to now use that 1 to get rid of the 5 and minus 1 beneath it. The operations that I want here are row 2 is row 2 minus 5 row 1, and row 3 is row 3 plus row 1, because that'll make both of those things be 0. So now we'll carry those out. You should check and make sure you actually get that when you work this out. And you see something we're developing here. So what I'm going to do is I'm going to divide row 2 by negative 1, or multiply by negative 1, whatever you want. It works the same way. And now we see that row 2 and 3 are the same. So if I do my next step of doing row 3 is row 3 minus row 2, I get something a little different here, which is a full row of zeros at the bottom. What does that mean? Well, that last equation now says 0 equals 0, so it tells us nothing. This third equation gives us no information. It also means that column 3 is not a pivot column. There is no leading entry in column 3. Therefore, column 3, or x3, is a free variable. So since column 3 is not a pivot column, x3 is a free variable. What does that mean? Well, it means that it can be anything. So for the sake of working these out and the way I like to handle these, let me just set x3 to be t. And so t for any value of t, we'll pick that to be x3, and then I can solve based on this t. So set x3 equal to t for any t. And we're leaving it as a variable now so I can adjust it later if I want to. What does that do? Well, let's write these two things that we have left as equations, see what we get. So as equations, we get the following. We get x1 plus 2x2 plus 2x3 equals negative 7. x2 minus x3 equals negative 4, and 0 equals 0. We already saw that this equation here does nothing for us. We've chosen to set x3 equal to t, so I can now plug that into both of these equations. So I have now x1 plus 2x2 plus 2t equals negative 7, and x2 minus t equals negative 4. Well, now I can solve for x2 and x1 in terms of t using what I have here. So this tells me that x2 is going to be negative 4 plus t, and plugging that up into the top here will tell me that x1 is negative 7 minus 2t minus 2x2, which is negative 7 minus 2t minus 2 times negative 4 plus t. So negative 7 minus 2t plus 8 minus 2t is 1 minus 4t. Then my solution here is x1 is 1 minus 4t, x2 is negative 4 plus t, and x3 is t for any t. And that's the most you can say here, and that is the best way to describe the solution because it does this for any value t you want to plug in. This will work. I plug in t equals 0, I get 1 minus 4, 0. That's a solution. I plug in t equals 4, I get negative 15, 0, and 4. Also a solution. No matter what value you plug in, this solves it out. So this is the best way to describe this answer. You could also write this in a vector form if you wanted. It would look something like x vector is 1 minus 4, 0 plus t times negative 4, 1, 1. And if you remember this idea from Calc 3 a little bit, this looks like a line in three-dimensional space. That's exactly what this is. The solution set here is an entire line in 3D space. If I have one solution, I get a point. If I have 0, I get nothing. But if I have infinitely many, I will get a line, or in some extreme cases, a plane, where every point in that line or plane is a solution. This is the way you can sort of visualize and write that in this form. There's an example of solving out a problem by row reduction where the answer is an infinite set of solutions and a way to formulate that as a line or parametric line in three-dimensional space.